Students, welcome to lecture number 11. So, we will discuss about electrical and magnetic properties of material here. So, as you have seen in the last 4 or 5 lectures, we are only talking about materials and their properties. Soon we will be taking over as the process of fabrication or synthesis of these materials. So, let us do some recap. So, we talked about electrical properties in the last lecture. Electrical properties are different types. So, like resistivity, conductivity is opposite of resistivity, band gap, dielectric constant, permeability, temperature coefficient of resistivity, many other things like thermoelectricity, superconductivity, piezoelectricity. We can't discuss all of this, okay, because there are many properties which will require detailed discussions, but neither will have time to do that nor is required, because many of the things can be learned from other lectures of NPTEL or textbook. So, basically what you are trying to learn is how to correlate these properties, so that mechanical or functional properties with the structure and in turn the ways things have been made, that is the processing of the materials. That is the idea, and we are trying to find out the connections between this, because finally when you use machine learning or deep learning model to find out materials with target set of properties, you need to know the properties which you are looking for, and you need to also know the important parameters on which these properties will be relying on or depend on. Like in case of strength, we know that why strength depends on grain size, strength depends on dislocation density, strength depends on defect structures. Similarly, many of these functional properties also will depend upon structure. So, which will deliberate more as you go on, but for the today's lecture we are going to talk about some electrical properties and magnetic properties. So, electrical properties means you are going to deal with conductors, insulators as well as semiconductors. So, conductors are ones which conduct electricity, like we know the copper or aluminum easily conduct electricity. Copper wire is widely used in the electrical appliances as to conduct as a conductor. Insulators are normally either polymers or ceramics, and they are basically kept between the conductor as well as the structure on which the conductors are placed, so that there is no leakage of currents. Like here you have a ceramic insulator in this picture, which is shown here directly. So, as you can see there, semiconductors actually are wide class of materials which are used in electronic industries effectively, and they are used to make chips, laptops, computers, everything, mobile phones, cameras, or even devices which use day to day life. So, they are relying on the semiconductor chips, and silicon is widely used as semiconductor materials, we know that, right. So, therefore, they are different class of materials which require different discussions than the electrical properties. So, metals are predominantly conductors. I have already given an example of aluminum and copper, and they have a huge conductivity, something like 10 to the power 7 of the order of 10 to the power 7 ohms meter inverse. That is massive high value, right. Compared to semiconductors, have a very low conductivity, like 10 to the power minus 4 to 10 to the minus 6 ohm meter per second. So, therefore, this is the difference actually, and most of the conductors, the conductivity does not depend much on temperature. On the other hand, semiconductors conductivity is strong function of temperature. Ceramics and polymers, as I said, they are insulators. So, they have a very low value of conductivity, and minus 10, minus 13, minus 14, right, and it can go even to minus 17. So, you have a range of conductivity 10 to the power plus 7 to 10 to the power minus 17 for all class of materials. Why it is so? We need to know that also. So, I put together all these comparison of resistivity. I discussed the last lecture also. The silver, copper, aluminum, gold have very high conductivity, so they have very low resistivity. Resistivity, remember, is a material property. Okay, we know that resistivity is nothing but resistance area divided by length, right, of the conductor. Therefore, this is a material property. Semiconductors have very low resistivity, so a little bit higher, not low. Low is for metals, and semiconductors have resistivity of the 10 to the minus 3 to minus 3 to plus 3, and Ceramics like window glass, silicon dioxide, they have very high resistivity of the order 10 to the power 17. So, therefore, you see the whole spectrum, and as we usually copper is a ductile, soft, can be easily made in different shapes, wires, conductors. So, therefore, that is widely used as a conductor material. On the other hand, the bonding there is metallic. So, as you know, metallic bonded materials have a huge amount of electrons available, freely available. On the other hand, silicon is basically hard, brittle, and it has covalent bonding. So, therefore, it has very low conductivity. Diamond on the other hand is almost no conductivity, very high resistivity. So, therefore, they are considered as an insulator. Well, so in order to understand this, we talked about how electrical properties of material depends on interaction of electrons with the materials containing these electrons. So, we can talk mostly about crystalline materials, that is why we discuss about Drude model, and Drude model is basically simple. It uses what? It uses the kinetic theory of gases. They consider electrons in a metal as a free gas or electron gas. It can move from one place to other place very easily, because these electrons are not perfectly bound to any ion or any metallic nucleus. So, therefore, they are free to move from one place to other place. Now, it is during the movement they collide with each other, they collide with the ionic core. So, this collision can be treated using a kinetic theory of gases. That is what Drude has done, and he discovered some relationships using this kind of assumption approximations about collisions, what happened between the collisions, what happened after at the time of collisions. I do not want to read about all these things, you can easily read through and discuss in the last lecture. So, basically what is the approach he used? He is telling that electrons are free to move. So, when they are moving, they collide with ionic cores, also they can collide with each other, and each collision will lead to change of velocity, both magnitude and directions. And this is something is important to measure what is known as a drift velocity, a velocity at which the electrons are drifting across the sample, and that drift velocity can be used to measure conductivity. So, there are a few equations there which we discussed in the last lecture, and we can actually determine conductivity, determine the drift velocity, determine the strength or the current, everything using those kind of relationship, and Drude model works nice. So, basically the collision is not very straightforward to be treated, like here it is shown a one simulated collision taken from the website of Harvard University. You can clearly see the electron can hit the ionic cores and change its direction many times before it reaches on the other side of the sample. So, what is important to know is the measure, how to measure the drift velocity at which it is moving through the sample. That is what will dictate the conductivity, and this is what the relationship current density J is equal to conductivity multiplied by electric field. So, conductivity is related to drift velocity, as we have seen in our last cases, and drift velocity is related to mobility multiplied by electric field, correct. That is what. So, exactly same kind of fields are shown here and there. You can see that net electron motion is possible when you have a collisions of electron with the ionic cores. So, these are the three fundamental relationships which we talked about. Drift velocity related to mobility time electric field, conductivity related to number of electrons into electronic charge into mobility, and this mobility can be converted using the top equations. Then you get this type of equation, and finally, current density related to drift velocity. So, drift velocity is a fundamental parameter in the Drude theory. It explains everything, but obviously there are a lot of failures. Major failure is coming from the conductivity value of different elements with different valency. Obviously, the element has a higher valency, more electrons will be freely available. So, n will change, the conductivity must change. But in the best of the metal, so have 1 or 2 valence electrons. So, their conductivity remain almost similar. Second thing which you cannot explain is the Hall effect. Hall effect allows us to determine the sign of the charge, whether it is a positive charge or negative charge, electrons or something else. But Drude theory assumes what? Electronic motion. So, but many metals shows, measurement shows many metals shows positive charge. So, it does not take care of that, and then it cannot explain thermal conductivity, specific heat of metal, thermal power, So, I just put a note at the end. Later on, Sommerfeld model, which modified the Drude model, suggested that which could explain some of the observation that could not be explained by Drude model actually. However, this model also failed to explain many other observations about metals, and hence a quantum mechanical model was developed. So, this classical model could not explain anything, but on a average this model provides you very generic relationships which can be used for all our purposes. And in quantum mechanics model, which is important to note is the Kronig-Penney model and a band diagram, which we will discuss now. And quantum mechanics is the base of many things, right. The quantum mechanics, electromagnetics and statistical thermodynamics, they are the three main pillars of modern physics. Quantum mechanics started in the beginning of last century, something around 1901 by Planck, who actually gave the quantum mechanics for the first time, and then it was used extensively in the literature. So, important aspect to understand quantum mechanics is wave particle duality. That means an electron can be considered as a wave as well as a particle. So, how it is considered as a wave? Because electrons can undergo interference. That is what gives you that it is a wave. Waves like light undergoes interference, that is what you see interference pattern or rather diffraction. But on the other hand, electrons actually also can behave like a particle. Very simple, electrons are treated in the orbital as a particle, right. So, charge and they are moving in the orbital as a particle. So, they can even tunnel through potential barriers. The first time de Broglie from France gave a relationship connecting the wavelength with the momentum. So, lambda, which is the wavelength any wave or electron wave, basically is equal to h, which is a Planck constant divided by momentum p. That connects both the particle and the wave, right. The wavelength is a wave property and momentum is a particle property. Momentum has a mass, right. So, particles have mass. We never consider wave as a mass. So, this connections was provided by de Broglie. His equation is of fundamental importance, and I know that is something which is widely used in quantum mechanics. But must say quantum mechanics is what? It talks about relationship of energy, like kinetic energy plus potential energy of a system keeps constant, and kinetic energy converted to p square by 2m. So, therefore, I can get a relationship like this, which is shown by the red box here. You see h cos square minus a square by 2m d2 psi by dx2 plus vx psi x is equal to e psi x. One can solve this equation to determine any wave functions, and once you solve that, you can find out probability of the wave functions. We can find out even the probability functions or integrator of the whole volume, that is integration minus infinity to plus infinity px dx, and that must be equal to 1, right, because it is a probability. One can also find out expectation values. So, these are all different methodologies or equations to find out the electron present at a particular place or at a particular time or not, but that is something which is easy for simple atoms like hydrogen or helium, but not at all easy for other metals which have a higher atomic number like copper, aluminum, iron is impossible. So, free electron model assumes there is no potential required for the electron motion. So, then you can solve this simpler equation where Vx psi x is not there. So, it is basically h cos square by 2m and del square psi x is equal to e psi x. So, once you can solve the second order differential equations, obviously it is a partial differential equation because its psi x depends on x and y and z, that is what makes life more difficult. Quantum mechanics was widely used to explain various kinds of things like photoelectric effects, Crompton effects. So, therefore, here I am showing you a snapshots of photoelectric effect. If you allow a light of certain energy, light means light particle has energy h nu is equal to h nu, right, and h is the Planck constant, nu is the frequency. So, that can be also written as h c by lambda, lambda is the wavelength. If a certain energy of light falls on a potassium, so whether it will be able to eject electron or not, that depends on the energy. When the energy is less than 2, it cannot, right, because 2 electron ball is rejected to eject the electrons. That is the energy by which the electron is bound to potassium atom. So, if you plus, or if you use energy less than that, it will not eject, only it will when it is more than that, it will eject. That is, so therefore, energy can be converted to wavelengths 550 nanometers or 400 nanometers wavelengths, and then it can eject an electron, and you can calculate even velocity at which the electron can be ejected also. So, as you see, limitation of the free electron model is that it seems all metal with same number of valence electrons will have similar conductivity value, but this is not found true. Solution is needed to incorporate the effect of ion present in the material in terms of the lattice actually, because it is not a one atom present in the whole material, many number of atoms are present in the material. So, how that can be taken care of? Well, so that is what we come to a situation of electrons in a crystal lattice, right. So, as you know, crystal lattice consisting of large number of atoms, and each atom is present as a core. Am I clear? So, therefore, each electron experiences a periodic potential. Why? Because you can clearly see atoms are present periodically, arranged periodically in a crystal lattice. So, as the electron moves, they see periodic potential like this. Am I clear? Even this way also. So, this kind of periodic potential it will see, it will be attracted to the, there will be attractive force between the core nucleus and the electron when it is near to the nucleus, and it will, there will be repulsive force when they are far away. So, therefore, we need to find out solution to the time dependent Schrodinger equation, that is more difficult. So, V r plus r equal to V r, where is the periodic potential, where r is the periodic distance, that is what will going to happen. So, as you clearly see, this is the distance in which the potential is repeated, right, that is what is a capital R, small r is basically function of r. So, hence this will be typical for my periodic potential. Am I clear? This is taken from standard physics textbook of, I think it is taken from standard physics, solid state physics textbook by Kittel, George Kittel. As you can clearly see, this is the potential energy u r, and these are the location of the ionic core. You can see that this is the location of ionic cores, and the electron potential energy will behave like this. So, these are the infinity values. When it electron is close to the nucleus, the energy will go very high. So, that is why this potential varies like this. Hence, typically any crystalline material will be periodic potentials, and it is plotted along a line of ions, along a line midway between the plane of atom. So, as you can see, solid curve is providing you the potential along the line of the ions, ionic cores, and dotted curve is what is this dotted curve, which is here. This is giving you the potential along a line between the plane of atom, and dash curve is giving you the potential of a single atom, right. So, this is the dash curve, this is giving you potential of a single atom, and this is giving you potential of what? Potential of the along the line between the planes of the ions. But just forget about it. Important thing you should remember is this variation, periodic variation of the potential, which I have drawn in the last slides. So, now the question is this: if I consider that kind of model, then energy will be given by E is equal to h cross square by 2m into k square, where k is nothing but twice pi by lambda is the wave vector, it is called a wave vector. Why it is called a wave vector? Because this is 1 by lambda. So, that means it is the inverse of lambda. So, if I plot now E as a function of k, it should look like this. That will be these are the energy levels. The electron can take any energy level along this parabola, right, because E is equal to k square, a constant h square by h cross square by twice m. You know, h square, h cross is what? H cross is h by 2 pi, right, that is what h cross. So, h cross is a constant, because h is a constant, m also is a constant, m is the mass of electron. Well, that is not actually constant, that will also depends on velocity, right, but still when you are not a relativistic regime, you can use m to be, you can assume m to be constant. So, then E is basically proportional to k square. So, that is a parabola, and you can clearly see that that is what happens. So, now as you know, electron also undergo the diffraction, right. So, therefore, there will be certain energy levels where electrons will not be present because of the Bragg's conditions to be satisfied. Bragg condition we know, right, 2D in sin theta is equal to lambda. So, in a fixed lambda, obviously when k is or there are certain lambda actually in which this condition will be satisfied. So, electrons will not present there because they will be diffracted. So, that is why there is a first allowed band, first allowed region where electrons energy can take there, and there is a second allowed band possible at a higher energy level, right. So, you can clearly see you are plotting is minus pi by 2a, minus pi by a to plus pi by a, right. A is here lattice constant, right. A is a lattice parameter, cubic crystals lattice parameter we have seen that A is a lattice constant. So, therefore, in between this you have forbidden energy gap or what is called a EG, right. And this is the reason why you have fundamental reason why you have energy gaps in crystalline materials. That is because of crystalline materials atomic arrangement is periodic, this happens because electrons will undergo diffraction or Bragg reflection will occur, and therefore, these actually called bands, different bands, first allowed bands, different allowed bands. Band means this is the energy level or the range of energies in which electron can take up for the free electron actually, by the way. So, that can explain the concept of energy bands in the material, and this is very important in semiconductor actually. You can change the energy bands very easily. So, I will not want to discuss further, but one can easily do quantum magnetic calculations and show how this energy gap will be forming because of standing wave formed at the zone edge due to Bragg's reflections. I am talking about Bragg reflection again because Bragg reflection is nothing but electron diffraction, right. Bragg's law is true for electron diffraction, X-ray diffraction, neutron diffractions, right. So, therefore, Bragg's reflection is responsible for these kind of energy bands present in the material. So, let us not go into all the details of mathematics because that will make your make you to do a lot of quantum magnetic calculations, forget about that, but understand the theoretical aspects of the whole situations. So, if I have to plot this, so you can clearly see this is how the energy levels are varying. These are the atomic positions. I have given 1, 2, 3, 4, 5, and this is how the electron energy level is varying, correct. Can you see that? So, now it is given here also, and this is the distance between the two atoms, correct, and this is the plot of distance versus potential energy. So, pile up of electrons at the ionic centers will happen. So, that is the energy density or the ionic density cos square pi x by a, and negative part opposite part actually is sin square pi x by a. So, therefore, active accumulation of electrons away from the ionic centers is very evident because that is why the plus charges will be happening, and near the ionic core there will be no electronic charge possible. That is obvious because otherwise ionic cores and electron will enter or attract each other and they will vanish, right, that does not happen, and UR is basically proportional to 1 by r distance. So, as we can actually do a quantum magnetic calculation and show that the standing waves actually interact each other or rather Bragg's reflections can happen because of these and interactions, and you will not have any energy levels in certain values of that. So, classically Kronig-Penney model talks about these aspects only, and what they do, they make certain assumptions further. What the assumption they do, these are the ionic cores and this is how the electron energy levels are varying. So, instead of curvilinear nature they assume like a very straightforward arrangements of that. So, what you do, you can solve the quantum mechanical equations, you can see this is the A unit cell. So, therefore, UI x is 0 in this region from 0 to A, and then it become very high here, then again it becomes 0, then again it become very high, then it becomes 0. It is a periodic potential, right, and this is a one dimensional lattice, remember that, but in a actual life it is a 3 dimensional lattice. So, calculations will be much more intensive. You cannot do it use your brain or something, you need the help of a computer, and this model was discovered along by 1939 Kronig-Penney, and this model allows you to calculate energy bands, as you can clearly see here. Now, energy bands are calculated, the first allowed band, second allowed band, third allowed bands, and these are the energy gaps which are known as a band gap. So, now we understand why semiconductors have band gaps, insulator has a huge band gaps. So, you need lot of energy for electrons to move from valence band to conduction bands. Valence band means the upper field, maximum field band, right. Conduction band means electron can jump to the band in which electrons are free to move. So, that is what we know classically. You can read any simple textbook, you will understand that. So, therefore, these allowed and forbidden bands which are plotted as a function of k is nothing but a wave vector, provides us all whole picture why how the electron bands can origin of the electron bands very easily can be provided by this concept. So, band theory is very important. In solid it basically its influence of the atoms in the solids can be taken care of. This model effect of periodically placed atoms in a crystal on the valence electron can be considered very easily, and we know it is basically a periodic potential which exists in the material, and then it can also explain why allowed and forbidden energy gaps can exist and band form energy bands can exist. Okay. So, that is it. So, in a nutshell I just want to put this picture, when there is no periodic potential, suppose you are running across a road, you can it is free to choose any length at which it can run, right, very simple. Any length means what? When you are running you have a step size. So, with this step size you can run any step size you can run, right. It does not matter whether you are taking longer step size or shorter step size, but when you have distinct obstacles sitting periodically on the path, you cannot take any step you want. You have to choose a specific length of step, otherwise you will hit these obstacles. That is what happened to electrons. So, electrons actually has to choose specific length or wavelength, otherwise it will reflect back or back's deflection will happen. That is in a nutshell is what is true. So, and that gives you this exactly this picture of band diagram, allowed and not allowed bands can be easily explained, and this is how the quantum mechanics can provide all the pictures. So, I just want to stop it here. I wanted to tell you how the energy bands forms. We will come back to next lecture where we will talk about little bit of band structure, mostly about magnetic properties of material. Thank you.